Welcome to my new calculus site. My name is John Gabriel, and in today's video I'm going to discuss misguided mainstream notions about Cauchy sequences and limits. And there are a lot of those, and I've discussed them in the past, but I think it's time for another perspective and perhaps a little more revision to those of you who already have studied the past articles, videos, etc. that I've published. So let's begin. Now, if you know the general term of a Cauchy sequence, or any sequence that converges, well, it doesn't have to converge. You can decide whether or not it has a limit if you know the general term. And you don't have to use the Cauchy definition at all. Now, interesting to note is that you cannot apply the Cauchy definition without a general term. Okay, so forget about trying to see whether a sequence converges if you don't know the general term. Now, let's take this example here, and you can see that if we compose our sequence from the terms of Sm, then you can rest assured that we can use this general term expression, which gives us S1, S2, S3, etc., to determine if it has a limit. Okay, if the sequence has a limit. And it's very easy because this here is the general term. Now, the definition of a Cauchy sequence means that for all epsilon greater than 0, there exists some n such that if little m and little n are greater than the distance between any of the terms in which a sub m and a sub n are used, it doesn't matter how many terms there are between m and n, then this will be less than the epsilon you choose. So supposing we choose epsilon is 0.1 here, right? As you see over here, where I'm pointing with my mouse. Then you can start n at 1, but if you move down the term to 1, you'll have a problem because you're still in the same term. So any term greater, you'll see that there's no problem. This 0.27, this value here, will always be less than 0.1, okay? So it doesn't matter how far you go. And it also doesn't matter if you're subtracting a6 and a7 or a2, anything greater than n, a2 minus a sub whatever. All right? So, and you can also change this function over here. Let's see if I can move this up a bit. You can change this so that you have here t of little x is equal to 1 divided by 2 to the power of x, like so, and you'll see that all these terms here will change, okay, the sequence terms. And so now this here is a problem because 0.125 is greater than 0.1, right? So we'd obviously have to do something about the terms or about e. Right, so if we move e along, then we'll get a correct inequality. But of course, all we have to do is simply ensure that after a given n, all the other terms are greater. So if we start at 1, anything greater than 1, the difference must be less than the epsilon, which is this value here, 0.09. And so in this case here, we'd have to make epsilon at least 0.13. Okay, and so this here is a demonstration, and I'll place a link to it in the details section. And this is really what it means for a sequence to converge. It's actually even irrelevant that this has been stated, because that's what a convergent sequence is. It's a term in which the distance between any of these two terms is less than the epsilon which you choose. And I show you in this article, which I'll also place a link, how we can do that. All right, and this is how we do it. So we just simply choose a little n, m is equal to m plus k, with k greater than 0, and so we have this condition here, right? And then we take the difference in distance, which is given by this expression here, and we consider what happens as k increases indefinitely, okay? And if k increases indefinitely, and you can read through this slowly in your own time, we'll see that the expression approaches this term here, which is what happens when k becomes very, very large or increases indefinitely. So we can choose epsilon to be greater than a sub n minus am, or we can choose it by observing the resulting expression in the limiting process. Now, be very careful. You cannot use the Cauchy definition in the case of finite differences, such as one finds in the derivative, without knowing the limit. And of course, it's easy to see this if we go to Dennis Muller, who's an idiot who's got an anti-side about me. He basically tries to show that this is rigorous but fails miserably. And so this is one of his pages here, and he says, then we call L the limit. But in order to know L, in order to work out if L is a limit, you need to know L. So there's no way that you can actually find L systematically in your bogus calculus, okay? And what that definition means is this, and L is the limit. That is, L is the derivative. And you can also download my free ebook to see all these details and much more. Now, notice that in a typical big, stupid, or mainstream academia site, such as Wikipedia, these two sections here are essentially the same. All right, a metric space definition is not different from in the real numbers. And there is, according to the big, stupid, a difference, because they think that just because certain sequences don't converge within the rationals, that they must converge to something else. Well, nobody knows what that something else is, because if it's not a rational number, then we don't know what it is, and there is no such thing as a real number. The hilarity of this bogus theory is that to define a real number, you already need to have a Cauchy sequence, which assumes that such a limit exists. Okay, so these two definitions here are identical. A metric is just basically a set with a distance function. Okay, and this dx sub m and xn is essentially the same as this. Okay, there's really no difference. And now, if you go to a university site, such as this one here in the UK, it says one of the problems with deciding if a sequence is convergent is that you need to have a limit before you can test the definition. And then they try to say Bolzano was the first to spot around the way this problem. Bolzano, the idiot, didn't spot anyway, and neither did Cauchy. All right, this here is still true in the case of the derivative. So, for example, in this case here, you still need to know L. There is just simply no way you can use this definition without knowing L. So, I just wanted to point that out to you and show you that these are several misguided notions in the mainstream. I mean, even professors like Wolfgang Muckenheim, who I respect, doesn't understand this and still insists that you can use the Cauchy definition for a derivative. Now, in your bogus calculus, you have no systematic way of finding the derivative. You have to use that flawed first principles method, which is obviously a load of garbage. Now, that's really all I wanted to cover in this video, and please subscribe if you're not a subscriber, and be sure to download my ebook. It is the most important mathematics book ever written. You will not only learn about the formulation of the new calculus, which doesn't have any of this nonsense. It doesn't use ill-formed concepts such as infinity, infinitesimals, or limits. And you will also see all the flaws in the mainstream mathematics and how they don't really understand what they're doing. And it's a shame, because a lot of students who want to study mathematics aren't able to accept these concepts, and they eventually end up either learning them rote and getting through in that way, or just abandoning the entire course that they're on, which is a shame. Okay, so that's it for this episode. I'll try to produce more again, as I said earlier, and I'm doing pretty good because I've produced 3 in the past week or so. And I'll chat to you again soon. Please leave me a question or 2 in the comment sections, but not more than that. And click like so that more people can learn this wonderful knowledge that I'm sharing with you. Okay? Very well. This is a new calculus channel. My name is John Gabriel. Until next time, goodbye.